Okay, so good afternoon, everyone. Hope all of you are doing well after the final competition run. Okay, so for the run, okay, I'm definitely very happy. All right, to see all of your robots completing the maze. Okay, if you had some expectations of how your robot should perform and did not do as well. Okay, don't worry. Okay, things do happen. Okay, over the past few batches, we have always had cases of groups where everything goes well, in the testing, but in the last minute, something just goes wrong. Okay, and you can't figure out what is the issue, and so you're stuck. Okay, so things like that do happen. All right, but uh, I think most of you did a good job. Okay, even if your robot did not do as well, I think important thing is if you think back to the beginning of the semester, all right, and if we when we told you that this is what you're supposed to do, all right, supposed to design your own IR sensors and do color sensing and write your own code to control motors and interface with sensors and all. It would have been a huge task, correct? Something that you could not have imagined. Okay, but now when you fast forward, the last 12, 13 weeks, and you see what you have achieved, I think it's a big thing, correct? I mean, those of you who have had some prior experience or knowledge, that would have helped, But for many of you, it's the first time you're dealing with circuits and building things with components and using the multimeter and scope and things like that. So it is definitely a huge achievement for all of you. All right. So, and I think that is important. Uh, so when you go on to next semester's EPP2, uh, you will also be as intense, all right, and as demanding as EPP1, all right. Normally we'll say EPP or CG1111, all right. They are both interchangeably used. Okay. In EPP2, when you go on to it next semester, you will still be building something, all right, a robotic system and interfacing different components and subsystems together. And the focus will be more on the software interfacing. All right. So there will be some hardware, all right, but the main focus would be to understand the software at a greater level, all right, or a deeper level, I would say. Okay, so that is for next semester. Okay. So for now, what we are left with is so for your project, you still have your report that is due. So please remember to submit that before the deadline. Okay. And yeah, so only one member needs to submit. All right. Not everybody needs to submit. Just one member of your team needs to submit the report. Okay, so make sure that in your cover page you already have indicated clearly your team member names and all your group name and subgrouping that you have been using the whole semester. Okay. Okay, so right now, what we will do for today is we will go through both the past year papers. Okay, there are a set of recap slides, but I will not go through that because it is nothing new. It is just sort of copy pasted from the uh, earlier prep materials that you have been using all the while. So it's nothing new there. So I think it's more value add that we go through the past year papers. Okay, so we'll start off with the 1819 paper first, okay, and then we'll move on to the next paper. Okay, so if you have not sort of done your revision yet, it is still okay. You just follow through with whatever I'm explaining. Okay, as usual, I will upload the video, all right, and send you all the links so you can always refer to it over the weekend when you pick up on your revision. Okay, so we'll first go through these few questions. So quiz 1 had some AC questions. And since AC was not covered in quiz 1, we just go through those questions first. All right, and then we go to the actual quiz 2 questions. Okay, so in this circuit over here, basically what you have is a AC source, all right, and you have two parallel branches here. One is a RL and the other is a RC. Okay, and you're asked to calculate the voltage VT. Okay, So as what we have taught you, basically once you convert your capacitors and inductors to the equivalent impedance, all right, then your DC circuit analysis principles actually apply, correct? So if you were to imagine, okay, so if I were to uh, sort of equate this to a DC circuit, okay, so imagine that the resistors, the two inductor and capacitor are actually resistors, all right, and I give you a current and ask you to find what is V. Okay, what you would have done is you would have grouped these two together, group these two together, and then find the total combined impedance, correct? And then you would have had a simplified circuit, okay, that looks like this. Okay, and one total combined resistance RT, and I times R would have given you the voltage value. Okay, so the same principle is what we're going to apply here. All right, and the only sort of challenging aspect is you're dealing with complex numbers, all right, because it's XR and XC. And as we said before, you should by now have figured out how to use the complex number features in your calculator. All right, I think most scientific calculators do have this feature. So go and figure out, if you have not done so, how to use it. So that will save you a lot of time, okay, during the assessment. Okay, so the first thing is the XL and XC. So XL is J omega L, which will be J. Okay, so the incoming signal is 10 cos 300t, so this is omega t. So omega is 300, so this is 300, and your L is 10 milli. Okay, 10 milli, so that will give me a value of 3. So J3. Okay, XC is 1 over J omega C, which will be 1 over J. Omega is again 300, and C is 1000 micro. Sorry. Okay. So that will give me minus J over 0.3. Okay. So with that, basically what you can do now is you can simplify at the first level to combine this circuit to two impedances. Okay, so this is Z1. I'll call this Z1, and I'll call this Z2. Okay, so Z1 will be 2 plus J3, correct? Because R plus J omega. And Z2 would be 3 minus J over 0.3. Okay, so now that you have two impedances in parallel, you can combine them together. How you do your normal approach using resistors, so it will be Z1 Z2 divided by Z1 plus Z2. Okay, so those detailed complex number stuff I will skip. All right, you can just key in your calculator and get the answer. So the answer should be 3.23 angle 12.1 degrees. All right, so effectively now what you have is you just have a single voltage source and a single impedance. It is ZT, and this is your I. Okay, so voltage, okay, is I is Z. So I is 10 cos 300t, so it will be 10 angle 0 degrees multiplied by this 3.23 angle 12.1 degrees. Okay, so that will give you 32.3 angle 12.1 degrees, which will be 32.3. Okay, so you can rewrite it in its actual form over here. So cosine 300t plus 12.1 degrees. So that's your final answer. Okay, so the omega is whatever omega that you see as part of the current flowing out of the source or the voltage source, that is the omega you will use throughout. Okay, because in our analysis we are using a fixed source, correct, with a particular frequency. Right, the only time when we say the frequency changes in the input signal, that is when we are talking about the filtering operations and so on. Right, that is where we have the uh, f changing. All right, but in this kind of normal AC circuit analysis so far, we assume that the omega is constant. Correct. If the omega is always changing, then all these calculations for XL and XC would not be valid. Correct, because XL and XC are computed based on a particular omega. All right, so that is why we analyze based on that particular frequency to be consistent throughout the circuit. All right, so with this, your answer would be D. Okay, for this question over here. Question 17. So this is actually a follow-up. So if you look at it, the values are all the same. All right, so that sort of saves you some time. Okay, so always look back and see, okay, whether the question is a follow-up or similar value. So that can save you a lot of time. All right, if by reusing some of the older calculations you already done. Okay, so in this question, you're supposed to given the I, and you're supposed to find IC. Okay, IC over here. So again, this is the same idea of the current divider rule. Okay, so if I have a DC circuit, all right, and I have two resistances. Okay, and I have a particular one. Sorry, it will be, so this is R1 and R2. So it will be, if I want to find I1, okay, if I want to find I1, it will be R1 over R1 plus R2 multiplied by I. Okay, so it is the opposite resistance divided by the total resistance multiplied by the current coming into both the branches. Okay, so the same rule applies here. So if I want to find IC, okay, so this circuit, okay, we already saw that we can simplify it into two impedances, right, which we have done in the earlier question, Z1 and Z2. Okay, and this is your I, and this is your IC. So IC would be Z1 over Z1 plus Z2 multiplied by I. Okay, so this is my I, the current coming in. Okay, so in terms of Z1 and Z1 plus Z2, I will let you all do that part. The current, again, you can just simplify it in this into its polar form here. All right, and then the rest is just your normal complex number. Okay, so the subsequent steps are all your complex number arithmetic, so I will not go through that. So the final answer would be 60.1 degrees over here. So you get 7.2 cosine 300t plus 60.1 degrees ampere. Okay, so that would be answer 8. Okay. Okay, so for this other question, so what you have here is you are given that you have a 100 ohm resistor connected in series with a practical inductor. So a practical inductor has a resistance as part of its inductance as well. Okay, and what we know is the phase angle of the resistance VRT is found to be negative 67 degrees with respect to the source voltage. And you are supposed to find the inductance. Okay, so basically we can apply the same concept as before, which is the voltage divider rule, correct? So again, if I look at a DC circuit, if I have one resistor here and I have another resistor here, this is R1, R2, and this is V. the voltage across R1 will be R1 over R1 plus R2 multiplied by V. Okay, so the same principle is what we're going to apply here. So in this circuit, VR is just a plain resistance, so no issues with that. Okay, for this, you have inductor, so you have 22 plus XL, right, R plus J omega L. So XL is J omega L, J omega L. And since you do not know L, you can write it as J omega L first. Okay, so omega we know from here, but okay, we can just keep it as omega first till the last part when we're going to do the actual calculation. So the L is the unknown that we need to find. Okay, so by applying this same voltage divider rule, we can say that in this case, VR is equals to 100 over 100 plus 22 plus J omega L multiplied by the source voltage here, which is 7 angle 0 degrees. Okay, so if I were to go through here, I'll get 700 angle 0 degrees divided by 122 plus J omega L. Okay, then if I were to, okay, so shouldn't have cancelled. 700 over 122 square plus omega L square root. Okay, and then you have the phase angle here. So the phase angle, okay, let me write it over here, is 0 degrees minus inverse tangent of omega L over 122. Okay, so this part here, this is the amplitude, right? This is the magnitude. Okay, and this is the phase. Okay, and what we are given is the phase, which is minus 67 degrees. So we can say that minus tangent inverse of omega L over 122 is equals to negative 67 degrees. Okay, and then from there you can solve for omega L 3, 5, 6, and then you substitute omega inside and you do your arithmetic. Your final answer for L will be 4.57 millihenry. So the answer here is C. Okay, so if you look at the last three questions, basically we are applying the same DC circuit analysis approach. Okay, only thing is right now we are dealing with an AC signal and we are dealing with impedances. Okay, so the only thing is the complex number part. Other than that, the same concept that we have learned, voltage divider, current divider, Ohm's law, all of them are still applicable here. This one, casual quiz 2 questions. Okay, so my internet connection seems to be a bit unstable. I keep getting that warning. So if I do get logged off, just stay in the Zoom. I'll come back in. Okay, so the first question is on the PMDC. Okay, it's connected to a 12 volt DC source. Okay, under no load condition, the motor speed is 1000 RPM. Okay, just give me a minute. Okay, so under no load condition, the motor speed is 1000 RPM. At a low torque of 1 Newton meter, the speed drops to 900 RPM. The armature resistance is 1. Okay, so let's look back at some of the basic concepts first. So we know that we have a voltage and that will cause current to flow through the motor, and the motor itself is modeled as a resistor, okay, followed by the shaft, correct, that is turning. Okay, and we also know that there is a back EMF that is generated while it's turning, and while it's turning, there is a torque shaft and the omega, the speed at which it is rotating. that we factor in. Okay, so there are also some formulas that you have seen concepts and tutorial questions. The same idea is what we're going to apply here. Okay, so the first thing is at 1000 RPM, it is no load. Okay, so at 1000 RPM, okay, it is a no load condition. Okay, so if you remember, when we say no load means it is spinning freely. All right, so at under no load condition, your current is approximately 0. Okay, and in that situation, okay, so if you remember the expression, we say Im is equals to Vm over Rm minus Ke omega over Rm. Okay, so in a no load condition, we say the current is approximately 0. So this expression can then be simplified as just Vm equals to K omega. All right. Since we always say that the both the K's are taken to be equivalent, we can just simplify it and write as a single K. All right. Now we can put in the value. So we can say that 12 Vm is 12 is equals to K omega. So omega here is given as RPM. So you need to convert it to radians per second. So it is 2 pi 1. That will give me a K of 0.1146. Okay, so that is the first step, finding out the K. All right, and then the next thing that we are supposed to look at is with the load torque of 1 Newton meter, the speed drops to 900 RPM. Okay, so at 900 RPM, okay, 900 RPM, what happens? Okay, the torque is given by this KIM, all right, and torque is 1 Newton meter here. K is 0.1146, and from there you can find your IM. Okay, so the current, okay, at 900 RPM is equals to 8.726 ampere. Okay, then the next thing you can also find is the back EMF. So back EMF is given by K omega, which is 0.1146 multiplied by 2 pi 900 over 60. So that will give me 10.8 volts. Okay, and with that, you can come back to this expression over here, where we say that Im is equals to Vm minus K. Okay, so Ke omega is basically your EB, right? EB over Rm. So I substitute, so I found Im. Okay, I know what is my Vm, I know what is my EB. I can now find my Rm. Correct, so Rm will be equals to 12 minus 10.8 over 8 8.726, which is 0.138 ohm. All right, so as you can see, basically what we are doing is we are going through the procedure step by step based on the formulas that we have. Okay, and the approach is quite consistent. Okay, so if you look at this question, plus if you look at earlier questions in your tutorial or practice questions, it's always the same approach. Okay, so as long as you understand, okay, what I need to do with the information is given. Correct. So under no load, what should I do? Under stall, what should I do? All right, and then how do I use the formulas correctly? Okay, then there should be no issue in solving these questions. Okay, so for this, the answer will be 1A, 0.138 ohms. Okay, so question 2. Next question for the PMDC. So again, we are having a motor connected to a 24-volt source. So we are given no load condition. So it's 2000 RPM, right? And load torque of 1 Newton meter, speed drops to 1800 RPM. So you can see it is quite similar, right? We are giving you some initial information and then we are giving you some new information. Right? So originally this is the VM, under no load, we have something. And once I add a particular load, okay, what is the torque and what is the speed? All right, and now we are wishing to operate it at a new RPM with the same load torque. All right, and we want to find out what is the required PWM duty cycle. Okay, so basically when you say, if you come back here, when you say no load, okay, no load means your torque is zero, right? Because your current is zero. Okay, so under no load condition, you say there's no torque because it's free running. Okay, but so you have different formulas, okay, that you need to use, okay, given the information only under different conditions. Okay, so let's look at this again. So the first part is at 2000 RPM. Okay, at 2000 RPM, what do you get? You get the same thing. So no load condition, if you remember, no load condition means your current is zero. So your VM is K omega. So again, the same thing. So VM is equals to K omega. So I can say that 24 is equals to K 2 pi times 2000 over 60. And that will give me a K of 0.1146. All right, similar to just now. And then the next information at 1800 RPM. Okay, you are given that you have a particular torque. So the torque is Ki. So torque is 1 Newton meter here equals to K, which is 0.1146 multiplied by I. And from there, you can calculate your I to be 8.726 ampere. Okay, and then the next step is, so you're running at a new particular or new speed with a load attached, correct? So now you can calculate the back EMF voltage. Okay, so EB is K omega, which will be K 0.1146 multiplied by omega, which is this current speed. So it's 1800 times 2 pi over 60, which will give me 21.6 volt. All right, so with this information, you can do like what we did just now. R is equals to 24 minus 21.6 over 60. All right, sorry, over current, which is 8.726, which will give me 0.275 ohm. Okay, so this is the same thing we did here, okay, where Rm is Vm minus Eb divided by current. So it's basically Ohm's law, right? If you look at the KVL, if I draw a loop here, this is your voltage source, this is a voltage drop, and you have a single resistance, correct? So you're just basically applying your Kirchhoff's voltage law principle here. Okay, and from there you can calculate your R. Okay, so now you have the whole picture ready. So the next step is we are given that we want to operate the motor at a speed of 1600 RPM for the same load torque. Okay, so if I'm going to operate it with the same torque, okay, so if you look at this equation here, if it's the same torque, all right, that means it is the same current. Okay, same torque means same current. So the only thing that will change has to be the voltage. All right, the only thing that will change has to be the voltage. So what will I have to do now? Okay, so the next step would be okay. So let me draw the circuit here first. Okay, so you have this. Okay, a motor over here. Okay, so you know what is your resistance, correct? Is 0.275 ohm. Okay, so with this resistance, you also know what is the current. Okay, so the current that is flowing is 8.726. So point multiplied by 8.726, you get a voltage of 2.4 volt here. Okay, And what is this EB now? So you can calculate EB, okay, by using the same formula here, K omega. So the new EB will be equals to 0.1146 multiplied by 1600 times times 2 pi over 60, which will be 19.2. So this will be 19.2 volts. All right, that means the total voltage that you need across the motor, okay, will be, so the total voltage will be EB 19.2 plus the voltage drop across the resistor, which should be 21.6. Okay, so I need to supply 21.6 volts, okay, to the motor. Then I will be able to get the same torque and run at a speed of 1600 RPM. Okay, so 21.6 volt is the voltage I need to supply. All right, but my main supply is still 24 volts and I'm using PWM. Okay, which means I need to do the on off cycling, correct? So basically all I need to do is take 21.6 divided by 24 and that will give me 0.9. So I need to run my PWM at 90%. Okay, that means 90% of the time it is on, 10% of the time it is off. Okay, and that would mean the 24 volt would step down to 21.6 volts. Okay, so the answer here is B. Okay, so that is as you can see, question 1 and question 2 quite similar, correct, in the whole process. Only thing the last part there is the PWM. Okay, but other than that, the way we use the formulas, the way we analyze is quite consistent. Okay, so in this question, so this is the other thing that you need to also know about the stall, correct? What happens when you stall the motor and there's current? So how do you relate to it at that time? Okay, so in this question, we are given that we have again a motor powered by a 12 volt DC source. Under no load, it is 2500 RPM. Okay, and when I clamp such that it doesn't spin, so when it doesn't spin means it is considered you are stalling the motor. Correct, so this is considered a stall condition. So under a stall condition, the motor current is 0.5 ampere. Okay, so when a vertical load is attached, the speed drops to 2000 RPM. Okay, so what is the current drawn by the motor for this load torque? Okay, so let's look at it step by step. So the first thing we know is that the stall current is equals to 0.5 ampere. Okay, so when it is stalled, okay, so let's write it. When it is stalled, okay, what do you know? We know that the back EMF is equals to 0 volt, correct? Because back EMF is K omega and omega is 0, correct? It's not spinning. Okay, so from there, if you look back at your equation here, okay, so if omega is 0, left is Vm over Rm, which means your equation Im is equals to Vm over Rm. So from there, you can calculate your R to be 12 over 0.5, which is 24 ohm. All right, so from this, you can calculate what is your resistance of your motor. Okay, so that is how you use the stall current information. Now, the next thing is your no load condition, correct? So under no load condition, what you have is, as before, what we said is Vm is equals to K omega. That is your no load condition. So your Vm, which is, so Vm equals to K omega. So 12 is equals to K omega, and that is 2500 RPM. So 2500 times 2 pi over 60. So K will be equals to 0.0458. Okay, and then at 2000 RPM, okay, at 2000 RPM, what happens? Okay, so if you draw your circuit again, okay, so you see that you have your current, you have your Vm, okay, and you have your resistor and your motor, correct? So now you know your resistors is 24 ohm, okay, and you have your motor that is going to be spinning, so that will generate a back EMF. Okay, so now what you need to do is you need to calculate how much current is being drawn. All right, so since you know your VM is 12 volt, so 12 is equals to whatever current IR plus your EB. Correct. So if you apply your Kirchhoff's voltage law, look here, 12 is IR plus EB, and I is what you're supposed to find, multiplied by 24 plus EB. EB is your K omega, so 0.0458, and omega in this case you're running at 2000 RPM, so it is 2000 times 2 pi over 60. Okay, and with that you can calculate your I to be equals to 0.1 ampere. Okay, so the answer here is D. Okay, so question 4 is quite a straightforward question, right? Nothing new here. So the formula that you basically need to use, okay, so basically we're relating, we're talking about the full wave rectifier, so we're relating the voltage and the resistance, okay, with the voltage ripple, okay, based on the frequency of the input signal. Okay, so the formula is a standard formula where delta V is voltage across the load divided by 2 FRC. Okay, so you put everything into the formula. So 0.9 is equals to 12 over 2 times 50 times 40 times C. And then you get C is equals to 3 0.33 millifarad, which will be equals to 3 microfarad, which is C. Okay, so there is nothing sort of tricky or anything here. It is just as long as you know how to apply the formula that relates the voltage ripple that you experience, then it's quite straightforward to solve this. Okay, question 5. Okay, so question 5 is on transformers. So basically you have a transformer over here. Okay, it is a step up transformer. So the secondary is connected to a load of 1500 watts. So here you have 1500 watt connected, and you have 600 volt. Okay, 600 volt RMS. The primary current is 12.5 ampere. Okay, the number of turns in the primary winding is 500. So there are 500 windings here. Okay, so how do you relate them together? Okay, so what they ask, what is this primary voltage? Okay, so basically for a lossless transformer, you can say that the input power is same as the output power, correct? So if the output power is 1500 watt, that means the input power is also 1500 watt. Okay, so power is voltage times current. So 12.5 times the voltage will give you 1500, and from there you can calculate this 120 volt RMS. Okay, so it is quite straightforward. Okay, if you try to calculate other ways, also is possible, correct? So for example, you can calculate the secondary current. Alright, you can say that, okay, since I know this is output power and this is output voltage, so I can relate it to secondary current. That will be 2.5 ampere. Okay, so in this case you can relate the formula Vs over Vp is equals to IPOIS, and from there you can also find your VP. You get the same answer. Okay, so rightfully, so far we have dealt with ideal transformers. All right. Of course, the question can always give you some variation and say that it's a non-ideal transformer, and then there is a 10% power loss, for example. Okay, so if there's a 10% power loss, then or something, then you can relate that to calculate and say, okay, how much should be the input power? Correct. That means the output power is 10% lower than the input power. Correct. So uh, in our analysis so far, we always assume it to be ideal transformers, ideal op-amp, and so on. Okay, so that is something that we have been using. Okay, but ideal, they'll give you some information on how to what to factor in. Correct. So if, for example, you say non-ideal, right, and then they say that the voltage drops by a certain percentage or the power drops by a certain percentage, then you factor that in when you do your calculation. Okay, so that is basically how you deal with situation where it is a non-ideal case. Okay, so okay, for next, so we have a transformer, primary winding is 100, the current in the primary and secondary is 4 and 28. Okay, and the number of turns. So in this straightforward question, that equals to 4 over 28 times 100, which will be 14.3. So approximately. Okay, so you need to. So it is a straightforward sort of question where you just apply the formula directly. Okay, nothing tricky here. Okay, so question 7. So question 7 is about our filtering operation. Okay, so it is again very similar to what we have seen in tutorials. Correct. Only thing in tutorial we go through all these steps. Okay. Over here you can come straight to the last few steps. Okay, where we just need to look at the formula that relates to the gain and the formula that relates to the change in the gain as the frequency changes. Okay, so if you remember, for a low pass filter, all right, the formula that we get, okay, in the end is given as, okay, the gain formula is given as this, 20 log to the base 10, okay, of whatever gain, minus 20 log to the base 10 of square root 1 plus omega CR square. Okay, so that is basically the final formula. If you look back at all the tutorial questions, that is always the formula we end up with. All right. This gain, of course, is a factor depending on whether you use active or passive. Right? If it's passive, the gain is just 1. All right? There's no amplification. If it's active, then it depends on the op-amp that you configure. Then this part is the what we call the pass band. Right? The pass band gain. Okay, and it is constant throughout the pass band. And this is the one that changes, okay, with omega or changes with frequency. All right, so this is the component where we will relate to it as the one that is changing. Okay, so here let's come back to the question here first. So in this question, we are given that we have recording in this particular frequency. So if I were to draw the, let's say, the signal waveform, okay, so between 195 and 395, so between 195 and 395 is the frequency of the audio signal. All right, and then but what he found was there was some noise. All right, and the noise is in the range of 4,000 to 6,000, so somewhere here 4K to 6K is where he has some noise. Okay, and he wants to remove the noise that he can reduce the, you can see that the one that you want is in the lower frequency and the one you don't want is the higher frequency. So what you want is to have a low pass filter. Okay, so you want to have a low pass filter. Now, the actual cutoff and all is not specified here, but what we know is at this point of time where it hits the 4 kilohertz. Okay, at this point is where you want the gain to have dropped by at least minus 18 dB. Okay, so that is the information you know. Okay, anything beyond 4 kilohertz, your gain is going to be even lesser than 18 dB, which is fine, correct? Because the minimum you want is 18 dB. And since your noise is starting at 4 kilohertz, at 4 kilohertz is where I must start to hit the 18 dB. All right. Beyond 4 kilohertz, you're going to get even lower gain. Okay, going down to 18, 19, 20, and so on. But that doesn't matter, correct? What you're given is a specification is the noise must be reduced by at least 18 dB. So the noise starts at 4K. So at 4 kilohertz, I must make sure that the gain has reduced by 18 dB. All right, so that is the objective. That means for this second part over here, I must make sure that it is hitting 18 dB at 4 kilohertz. Okay, so that is the part you need to focus on. So it is minus 20 log base 10, 1 plus CR square must be equals to, so at F is equals to 4K, it must be equals to minus 18 dB. Okay, so the rest is the same as your tutorial. The rest is the same as tutorial. Will be 10 to the power. Okay, then from there you get omega CR is 7.88.88 over omega, it is 2 pi 4K, and that will give me 3.14 times 10 to the power minus 4 seconds. Okay, so your CR is this. So basically what you need to do is look at all these possible options and see which one gives you a CR of 3.14 times 10 to the power minus 4. Okay, so the answer would be B. Okay, so of course in your tutorial, we say that if you're designing on your own, you choose your RC, the R value based on that. Okay, so in this example, what they have given us is they've given us already pairs of RC values. So you need to see which RC pair gives us the correct combination. Okay, so a value of R with 3.314K and C of 0.001 microfarad will give me this RC value. Okay, so as you can see, it is the same thing we did in the tutorial, nothing different. Okay, the same concept, the same thing. Okay, you have a signal that you want, you have some signals that you do not want, and for the signals that you do not want, you want to reduce it by a certain dB at a particular frequency, correct? So as long as you understand that concept and how to apply the formula, then it's no problem. Right? It's the same thing, the exact same thing we did in tutorial. We're given a band pass filter. Band pass filter has two frequency components, correct? So let's draw it out. So the two frequencies are 600 and 1600. So this is 600 and this is 1600. Okay. Now, when I look at this bandpass filter, basically you must firstly know that this refers to your low pass. So this is your low pass filter. Your R is on the straight line and your C is going down to ground, and the C and R combination the other way around, that is your high pass filter. Okay, so that's the first thing you must understand. Now the next thing you must understand is a band pass filter is a combination of the low pass and high pass, correct? Alright, but you have to remember that it is high. So the cutoff frequency for the high pass filter is actually the 600 hertz. Cutoff frequency, that will be your 1600. Okay, so this is your high pass and this is your low pass. Okay, so that is the thing you understand. You're combining the high pass and low pass together, but the high pass cutoff frequency is actually the lower cutoff frequency, and the low pass cutoff frequency is actually the higher cutoff frequency. All right, so with that understanding, we can say that the so this is your cutoff frequency for high. You know that it's just a matter of frequency calculation is the same, 1 over 2 pi RC. So it's 1 over 2 pi. In this case, for the high pass frequency, it is R2 multiplied by 22 nano. Okay, and that must be equals to 600 hertz. Okay, so that will give me R2 value of 12057 ohm. And for the FL is the same thing, 1 over 2 pi R1 and 100 nano. That will give me 1600. Okay, and R1 will give me a value of 995. Answer for this would be 8. Okay, so the band pass filter we have seen before in the studio. All right. So as long as you know how to relate the two different cutoff frequencies and know which one is high pass, which one is a low pass, then it is easily doable. Okay. Now let's go on to question 9. So this question 9 is quite similar, very similar to the one of the questions in your additional practice handout. Okay, so you're supposed to calculate the current I out. Okay, so the first thing is we need to start applying the golden rules. Okay, and if you look back at your practice handout, you're also given a hint for the question that you can use the node voltage analysis approach. Okay, so let's look at it first step by step. So the golden rules say that there is no current flowing in, and in a closed loop configuration, V plus and V minus are the same. All right, so let's look at what is clear, what is obvious. So if I look at this point over here, okay, we can say that the voltage over here is actually a voltage divider. Right, because it's 10 volts going into 8K and 2K. So this voltage here is basically okay, 2. Okay, so the voltage here is 2 volts, which means that the voltage here at V minus is also 2 volts. Okay, because the op-amp golden rule, correct, that both the V plus and V minus will be the same. So if V plus is at 2 volts, V minus here, this node here is also at 2 volts. Okay, so that's the first thing. Now the next thing is, for this part over here, what we can do is we can do your node voltage analysis. All right, so let's look at this step by step. So since this point here and this point are shorted together, this point over here is also V out, all right, because it's connected together by a short circuit wire. All right, so now let's do a node analysis. So I'm going to call this VA. Okay, so for VA, what is this node over here? What is the expression I can get? Okay, the expression I can get is, okay, so what is the current flowing in? This current here would be 8 minus VA over 2K plus this current coming in would be plus V out minus VA over 2K plus this current coming in, which is 2 minus VA over 2k will be equals to 0. Okay, and since all is denominator is 2k, I can remove that and I can simplify it to say 10 minus 3 VA plus V out is equals to 0. Okay, this can be my equation 1. Okay, so that is for the first node over here. All right, and I can do another expression here for this node over here. So this node over here, basically you can say that VA minus 2 over 2K, that is for the current going into this node over here, plus the current coming down from V out. Okay, so it's V out minus 2 over 2K will be equals to 0. Okay, so this node only got 2 branches because there is no current flowing into the input of the op amp, so you can ignore that. Alright, so with this you can simplify this to say you get VA equals to 4 minus V out, and this is your equation 2. Alright, so I take equation 2, put into equation 1, then I can get 10 minus 3, 4 minus V out plus V out equals to 0. So I will get V out equals to 0.5 volt. And if V out is equals to 0.5 volt, I is 0.5 over 2K, which is 0.25 milliampere. The answer here is D. Okay, so the way to approach this question is again going back to the op amp golden rules, but you now need to apply what you learned earlier, which is the node voltage analysis. Okay, node voltage analysis, again, you look for nodes where you can form equations, and the whole idea is you want to form equations so that you can sort of solve for the unknown, all right, and then help you to find out something that is unknown in the circuit. Okay, so in this case, all right, we have 2 equations and we're able to substitute, and then from there we can find your V out. Okay, once you find V out, you can find your I out. Okay, so let's look at this question here, question 10. So in question 10, okay, so we have 2 op amps, both of them supplied with a dual power. Okay, so let's look at it step by step. So for this first op amp over here, the negative is 1.5 volts, which means that this node here, V plus here, is also 1.5 volts. 1.5 volts. Okay. Now, with that, what we can do is we can step by step find the current that is flowing in all the branches. Okay, so the current that is flowing in this branch here, okay, current is equals to 1.5 over 1.2K. Okay, which is 1.25 milliampere. And since no current flows into the input of the op amp, the 1.25 milliampere is also flowing in this 3.6K branch. So it's also 1.25 milliampere. All right, so the voltage over here at this point would be 1.5 volts plus the voltage drop across the resistor over here, which is 1.25 milli multiplied by 3.6K. Okay, and that will be 6 volts. Okay, now the next step we can do is, okay, current does not flow into any of the input branches of the op amp. That is one of the golden rules. Okay, so we do not need to worry about any current flowing into any of the branches that are directly connected to the plus and minus of the op amp. For this second op amp over here, we can see that the plus is connected to the ground, which means the negative is also grounded. So this is considered ground. So this is considered 0 volts here. Okay, so with that, you can and you have 6 volts over here. Now what I can do is I can now find the current. So again, we know the 1.25 milliampere flows inside this branch. All right. Now, what about the current that is flowing in this branch over here? Okay, so we can now calculate this as I is equals to 6 minus 0 over 8.2k, which will be 0.73 milliampere. Okay, so the current that is flowing through this particular branch, the 8.2k branch, is 6 volts over 8.2k. Okay, and since again no current flow into the branch of the negative terminal, this 0.73 milliampere has to go only in this upward direction here. So that's the only direction it can go. Okay, there's no other path for it. So from there you can calculate that the V out over here will be equals to 0, because the 0 volt is here, minus the voltage drop across the resistor over here. So it is 0.73 milli multiplied by 4.1k, and that will give me negative 3 volts. Okay, so basically the way we have solved this, okay, is basically applying Ohm's law again and again. Right? Ohm's law and your basic principle of how a voltage drops across a resistor. Okay, so if you look at it, we start off with the leftmost op amp, and we say negative is the same as positive, so 1.5 volt comes here. Then I calculate the current through this. All right, and since the current through this resistor is the same as the current through the 3.6k resistor, I can now know the voltage at this point over here. Correct. And since I know the voltage at this point, I can now find the current going through this branch by again applying Ohm's law. Correct. Current is basically voltage difference across the resistance. And since I know the current through this branch, this current is also going through this branch. Okay. And then from there, I can again apply the idea of Ohm's law. So the voltage, okay, at this point is, or the current flow is basically the voltage difference across the resistance. Correct. And then I can calculate the final voltage over here. Okay, so in this case, the dual power supply of plus minus 8 volts has no significant impact, but basically why it tells you that it is uh, why this is information is important is it tells you that the voltage of the output of the op amp can be both positive and negative. Okay, so if your op amp was not so this sort of gives you the information that since you have a dual supply, the output of the op amp can be both positive and negative. So that's why the negative 3 volts makes sense, right, in this case. Okay, so this next question on the op amp is also very similar. All right, you're going to do it again step by step. Okay, the only thing is, of course, now you have a AC signal, okay, as the V in, but the idea behind it is still the same. Okay, the idea behind it is still the same. Okay, so let's look at it step by step. So the first thing is we apply what we know on this 9 volts supply over here. We have a voltage divider. All right, so the voltage at this point over here is basically 2.2k divided by 2.2k plus 6.8k multiplied by 9. All right, and that will give you 2.2 volts. So this voltage here is 2.2 volts. So if this voltage here is 2.2 volts, then the V minus here is also 2.2 volts. Okay, so since your voltage here is 2.2 volts, then from there you can calculate the current here, I, to be equals to V in minus 2.2 divided by 4.7k. All right, and then from there you can see that whatever current that's flowing through this 4.7k is the same current that's going to flow through the 8.2k, correct? Because nothing is going to go in here. Okay, which means that the V out is equals to 2.2, which is the voltage here, subtract 8.2K multiplied by the current I. Okay, so VR is 2.2 minus 8.2K multiplied by I, and I is given as V in minus 2.2 over 4.7K. Okay, so the rest of it, okay, is just substituting and simplifying and so on. All right, so maybe I'll just show you a few steps here. So 2.2 minus 1.745 V in minus 2.2. So you'll get 2.2 minus 1.74 plus 3.838. Okay, then you substitute in. Okay, so basically 2.2 and 3.838, you get 6.038 minus 1.745. So what is V in? V in is this whole thing here. Correct? So it is 1.5 cosine 100t plus 2.2. Okay, so then you put in everything. Okay, and then finally you will get 2.2 plus 2.62 cosine 100t plus 180 degrees. Okay, so the rest of the step in between, I will leave it to you to try it out. Okay, so as you can see, in this case, V in is a AC signal. All right, so you can, I mean, if you substitute in V in from the beginning, then of course you have a much more complicated expression to deal with. Correct, so you try to keep it as V in, all right, and then towards the end you can substitute and solve it. All right, so that will help you to simplify your workflow, all right, instead of having to deal with so many numbers and everything from the beginning. Okay, so that is your, so the final answer for this would be A. Okay, 11A. Okay, let me go on to question 12. So question 12 is okay, so it's a question on sampling. So basically you have vocals in the frequency of 200 hertz to 400 hertz, and the Nyquist engineer, sound engineer needs to set up the music editing software to enter the Nyquist rate. Okay, so again, like I said before in the studio, you must be very clear on the Nyquist rate and Nyquist frequency. So there's two things, all right? The Nyquist rate is basically your sampling rate, which is the other one is your Nyquist frequency. Nyquist frequency is basically the highest frequency component. So read the question carefully and know whether you're asking for Nyquist rate or Nyquist frequency. So for Nyquist rate, you just know is a sampling rate, which is 2 times the Fmax, and since the Fmax is 400 hertz, 2 times of that is 800 hertz. Okay, so as long as you know the distinction between Nyquist rate and Nyquist frequency, then this question is quite straightforward. Okay, so in question 13, you are given that you have a rotary encoder that operates in the frequency range 15 hertz to 120 hertz. Okay, so between 15 hertz to 120 hertz, okay, you have a encoder, and the optimal fuel consumption occurs when the wheel rotation and the frequency of 30 to 60. Okay, so somewhere between 30 to 60 is where these readings tells you that optimal fuel consumption is happening. Okay, so basically what is happening is you have an encoder that is wide frequency range. Okay. Okay, so in this case, okay, you have to be careful that the highest frequency component is 120, all right? 30 to 60 is just there to confuse you. All right, the 30 to 60 is there to confuse you. Because basically it is telling you 30 to 60 is the data that tells you that the system on, you need to make sure you capture all the signals. Make sure I sample. Okay, my sampling rate would be 240, correct? So that is your Nyquist rate, sampling rate. But Nyquist frequency is basically the highest frequency component of your signal, which is 120 hertz. So the Nyquist frequency is 120. All right, so these kind of questions you must be careful. All right, there can be, like I said, the 30 to 60 is just there to confuse you, so you must be careful to understand the question and be careful of what is important, what is really, what are they really looking for. All right, and then you answer. Okay, so question 14 over here. So in question 14, a young engineer tested a sensor. Okay, he built a proximity sensor circuit. Okay, so give me a minute. I think the circuit is missing now. Wait. Okay, so this is the circuit. Right. So he built this proximity sensor circuit, okay, to detect. All right, and he wanted the circuit to light up one LED when an opaque object is less than 4 cm from the sensor, and another LED when it's more than 4 cm. Okay, so the important thing is, okay, so if you look at this waveform here, you need to understand the 4 cm, what does it relate to? So if you draw a line 4 cm up here, you can see that it goes directly to 3.6 volts. Okay, which means that for your circuit over here, all right, what you want to do is you want to be able to detect and differentiate between the 3.6 volts. Now, if you see down here, this resistor divider network here, R1, R2, is going to apply the same voltage to the V plus and V minus of the two different op amp. Okay, and what we want is, we want this voltage to be 3.6 volts. Okay, now when will each of these LEDs on? All right, so if I look at this here, if I look at this second op amp over here, you can see that the signal from the IR detector is connected to the plus. All right, so both of these op amps are connected as comparator mode, all right, because there is no feedback. Okay, there's no feedback. The plus and minus are connected, all right, separately, and we are using the output. Okay, we're using the op amp as a comparator. So it's connected to the IR detector's voltage. So for the second op amp, if input signal is greater than 3.6 volts, then I will on the LED. Okay, if my input signal, because my input signal is connected to the positive, okay, it's connected to the positive of the op amp. Alright, and the 3.6 is connected to the negative of the op amp on LED 2. For the LED, for the op amp 1, what you see is the 3.6 is connected to the positive. Okay, so when your input, okay, is lesser than 3.6 volt, that means 3.6 volt is greater than the input, then it is on. Okay, because the input is now connected to the negative and this is connected to the positive. All right. So this is the current configuration that you have here for this circuit. Okay. Now, what we want is light up one LED when it is less than 4 cm and another LED when it's more than 4 cm. Okay. So now we can relate back to the circuit and we know that LED2 will light up when my input is greater than 3.6 volt. So if you remember, if it's greater than 3.6 volts means it is greater than 4 cm. Correct. So when it's more than 4 cm means it's also more than 3.6 volts. Okay, which is relating to LED2. Okay, less than 4 cm, this is relating to LED1. Okay, so what you need to do is you need to first make sure that we choose a resistor combination. So instead of looking at all the options, first thing that you need to look at is which resistor pair combination will make sure that it is 3.6 volts. So if you can see here, this point is a short circuit point, correct? That means basically it's a voltage divider rule. So as long as I see R2 divided by R1 plus R2 times 5 must be 3.6. Okay, so this is the first thing you must do. Which R1 R2 combination will make sure that this is 3.6. Okay, and then you can see that if I put 6.8, so that means the combination will be R2 is 6.8. Okay, R2 is 6.8. Okay, so there's only two options now, B and D. Okay, so from these two options, you need to see which one is correct. Okay, so we can see that when it is lesser than 4 cm, LED1 light up, which is this, and if not, LED2 will light up. Okay, so that is based on our analysis of the circuit just now. So from there, we can know that the correct answer here is B. Okay, so that is how you approach this question. First, you find how the circuit is, do the second level of analysis, and then you know what is the correct answer. Okay, so that is your question 14. Now let's go on to the last question, question 15. Okay, so in this question, you are given this humidity sensor that operates according to this. And what we want is, okay, so this relative humidity basically changes, all right, in percentage levels. If it is VR is to be amplified by a non-inverting amplifier before being sampled, which one of the following amplifier design optimizes both the sensor operating range and the Arduino ADC range? Okay, so the first thing is, what is the maximum Vout? All right, because what we are saying is this. Okay, we are going to design an amplifier. So in this question, we're going to design an amplifier such that the output is going to go into the ADC of the Arduino. So the ADC of the Arduino has a range of 0 volt to 5 volt. Now what we want range of the op, so we can now design the amplifier such that after I amplify, the range becomes 0 to 5 volts. It becomes 0 to 5 volts. So what is the maximum value that the sensor can give me? So the maximum value the sensor can give me is when my humidity is 100%. Okay, so the maximum voltage V out Okay, so I think it's an internet issue. Let me explain again. So the what we are designing here is we are having an amplifier, all right, and the whole idea is you're having a sensor, we're going to pass it through an amplifier, and the output of the amplifier is going to go into the ADC of the Arduino. Okay, the ADC of the Arduino has a range of 0 volt to 5 volt. Okay, so that part we know. Now what we need to do is we need to figure out my sensor itself, what is the range of values that it gives me. Okay, so once I know the range of values it gives me, then from there I can know the amplification level that I need to make sure that it can boost to 0 to 5 volt. Okay, so the first thing is what is this maximum? So the maximum voltage, if I look at the formula, yes. All right, so that is at 100%. So when I substitute 100% inside, so it's 5 volt multiplied by 0.00474 times 100 plus 0.2354. So that will give me 3.547. Okay, so now we know that the maximum value is 3.547 volts. Okay, so at the input side, I had 0 to 3.547. The output side, I want 0 to 5. Correct. So basically, if I look at it, the gain that I want, that means the gain of the op amp must be 5 minus 0 divided by 3.547 minus 0. Right, the output range divided by the input range. And that will give me a value of 1.41. That means must amplify the signal by 1.1 will be amplified to become 5. So I will be able to maximize the full range of the ADC. All right, and since we know that we are using a non-inverting amplifier, so we can say that 1 plus RF over RI is equals to 1.41. So RF over RI is equals to 0.41. So what you need to do next is to look at the values of RF and RI, okay, to get 0.41, and that will give me 1.1 and 2.7 k here. Okay. Okay, so for simplicity's sake, you can say that you can just look at the maximum values, but rightfully you should look at the range. All right, but of course, looking at the range can lead to other issues to deal with. All right, but since we so I mean this question, yeah, I think yeah, it's easier to look at it from the maximum perspective. All right, then you get the value. If you look at it from the range perspective, your answer will be a bit different. All right, because your starting point is not 0. All right, and if your starting point is not 0, then there are other things you need to do. Okay, but that is not covered in your module. All right, so I think you simplify it. You just look at the maximum values. All right. Again, why I say it is this question is a bit incomplete. All right, is because yeah. So the V out, because the V out minimum value would be when the relative humidity is at 0%. But when the relative humidity is 0%, okay, you still have some V out voltage, correct? It will not be 0. All right. So what would happen is you need to factor that in your design. All right. But again, I don't want to go into that and confuse you. Okay. So to make things simple, you can just take the maximum values. All right. And then use that in your calculation. So you can just take 5 over 3.547 to be the gain that you want. So you just take the maximum of your sensor and maximum of your ADC, and from there you know what is the gain required for the op-amp. Okay, so this range doesn't start example here, so you just take it from maximum. Okay, so that brings us to the end of this question, this paper here, 1819 paper. Okay, so let's have a break. Let's give ourselves a 10 minutes break. Okay, we will come back and then we will do the next 1920 paper. Okay, so now it's 3:30, so I'll see you back here in 10 minutes time. Okay, and then we will do the next paper. Okay, so as before, we will first complete some of the AC circuit questions. So many of them are quite similar approach, similar idea. All right, so you find that is sort of a repetition, correct? So as long as you understand the idea, the way to approach the questions, then I think there will be no issue in doing the paper. Okay, so these are the questions from the quiz 1 of AY 1920. So in this circuit, you are given again two parallel branches, RL and RC, and you are given VC, right? And you are asked to find the voltage. Okay, find the voltage here. Okay, so how do we go about doing this? All right, so the first thing is we can see that both these branches are parallel, correct? So the V is applicable to both the RL branch as well as the RC branch. Okay, so if I were to first, let's just put aside the RL branch and we just look at the RC branch. Okay, so the same voltage is applicable, and let's say that I have both of them as resistors R1 and R2, and if I give you a voltage across R2, by voltage divider principle, we can say that the voltage across R2 is equals to R2 over R1 plus R2 multiplied by V. Okay, so with that same understanding, okay, we can approach this question. Okay, so the first thing is we know that this is a capacitor, so we can find XC. Okay, so XC is equals to 1 over J omega C, which is minus J over 100 into 100 micro. Okay, and that will give you minus J 100. All right, and applying this same technique over here, we can say that XC over R plus XC multiplied by V is equals to VC. Okay, this is C. So minus J 100 over 30 minus J 100 multiplied by V is equals to VC, and VC is 10 angle 0 degrees. Okay, then from there you can calculate V to be equals to 10.4. Okay, so the rest of it, again, you can use your complex number features in your calculator to simplify and get it done quickly. So you'll get 16.7 degrees. So the final answer will be 10.4 cosine 100 t plus 16.7 degrees. Okay, so the answer here would be C. Okay. So again, very similar circuit to the previous paper. Only thing is they just change the application of a different voltage law. Okay, so in this circuit here, again, the same circuit, all right, you're supposed to find the current I. Okay, so the current I. So how do you find the current I? So what we can do is, since we know the voltage, all right. That is, give me a minute now. Okay. Yeah. So since I know what is VC, okay, I can find this current IC, correct? Because IC is VC over XC. Okay, XC we have already found earlier, it is minus J100. Okay, and VC is 10, okay, angle 0 degrees. So this is minus J100. Okay, so minus J100, if you convert it, you get 0 degrees angle. So you get 0.1 angle 90 degrees. That is your IC. Now, again, looking back at our current divider rule, you can say that if I know to find the current in this branch, I take this particular branch impedance. Okay, so if you remember, again, let me draw it. So if I take I2 here and take I, okay, so I can say that the current through the branch I2 is Z1, Z2 is Z1 over Z1 plus Z2 multiply by your I. Correct? That is your current divider rule. So the same thing we can apply here. So we know that the current through this branch I2 is basically this IC 0.1 angle 90 degrees. So to get this current by applying the current divider rule, I can take this concept of Z1 over Z2 multiplied by the total current coming in. Okay, so in this case, Z1 will be 20 plus J10 over 20 plus J10 plus 30 minus J100 multiplied by the I angle theta would be 0.1 angle 90 degrees. Okay, so it's the same current divider rule, okay, that we are applying here. Okay, the opposite impedance divided by the sum of both the impedance multiplied by the incoming current. Okay, so the rest is again your complex number part, which I will leave it. Okay, so the final answer here is 2.5 degrees. So you get I TS 0.46 cosine 100 T plus 2.5 degrees. So that is your option C here. Okay, so the next question here. So again, very similar. As you can see, previous paper was practical inductor. Here is a practical capacitor. Okay, where we say there is a capacitor, and we are given that VR is found to be having a phase of 43 degrees, 43.6 degrees. So it's exactly the same thing as just now, correct? So if you have two resistors, R1 and R2, and this is V, if I VR2 is equals to R2 over R1 plus R2 multiplied by V. So the same thing. So first thing I need to do is to find out my XC. So Xc is 1 over j omega c, which is minus j over 100 c. Okay, so the omega is 100, the c is what you're supposed to find, and you can apply the same voltage divider rule, which says that 100 divided by 100 plus, so it's R2 divided by R1 plus R2. So 100 divided by 100 plus 5 minus j over 100 c is equals to your VR angle 43.6 degrees. Okay, so this is what you have. Now, in terms of, so this is multiplied by V, correct? Multiplied by V. V is 7 angle 0 degrees. Okay, so let me carry on here. So the expression will be as such, 700 angle 0 degrees divided by, so you have a magnitude, which is your 105 square plus 1 over 100 c square. Okay, and then you have an angle. In this case is inverse tangent negative 1 over 100 c divided by 105 equals to okay, so that is your expression. That is equals to your VR angle 43.6 degrees. All right, so again, as before, we are going to just focus on the phase angle because that is the information we are given. So the final angle here, 0 degrees minus inverse tangent of minus 1 over 100 c over 105. Okay, that will be equals to 43.6. All right, and then you get 1 over 100 c and 105 will be equals to tangent 43.6 degrees, which is 0.952. Okay, and then from there you can solve C to be 100 microfarad. Okay, so I mean the rest is all maths. I think the first step is to understand that we are basically applying a voltage divider principle to solve this. All right, so it is the same thing over here where you have two resistors. All right, and the voltage across one is the resistance divided by the sum multiplied by the source. Okay, the only thing here is it is because it's inductors or capacitors, we have a complex number that you have to deal with. All right, and since the information given is the angle, we focus on the angle. All right, to find the unknown component here. All right, so of course, if the information given was the magnitude, correct, then you compare the two magnitudes. Correct. So instead of focusing on the angle part over here, you would have focused on this part. Okay, so depending on what is the information given. So if you're given angle, then you look at the angle part. If you're given the magnitude, then you look at the magnitude part. All right, and then from there you can relate and then you can solve. So we have a PWM control PMDC motor powered by a 12-volt supply. Okay, the torque is 30 and the motor driving at 2000 RPM with 90% duty cycle, and the duty cycle is now reduced to 60% while the load remains the same. Okay, so let's look at it step by step. So first thing is we are given the torque constant K is 0.03, and we are now driving. We are given that when you are driving the motor at 90% duty cycle, okay, the speed is 2000 RPM. Okay, so so since my supply voltage is 12 volts, so you have to remember 100% is basically 12 volts. So which means 90% is 10.8 volts. Since we know that the actual voltage being supplied to the motor is 10.8 volts, so we can now apply our formula. So V is given as K omega okay, which is your back EMF voltage plus your IR, correct? So with that, you can solve, okay, for your okay. So let's solve for what putting what we have first. So we have 10.8 volts plus sorry, equals to k 0.03 omega 2 pi 2000 over 60 plus your IR. Okay, so this is so when you solve for IR, you'll get 4.517 volts. So this is basically the voltage drop, okay, that is experienced across the internal resistance of your motor, okay, while you're running at 2000 RPM with 90% duty cycle. Okay, now you have to remember that when the load remains the same, we say that the current is the same, correct? Because if the load is the same, means the torque is the same, so the current is the same. So if the current remains the same and your internal resistance of the motor does not change, so when your load is the same, this voltage drop across the internal resistance will remain the same. Correct? This 4.517 volts will still remain the same. So when I running at 60%, okay, when I'm running at 60% of the duty cycle, my voltage would be 7.2 volts. Okay, so this is just a ratio, right? So for 100% is 12 volts, so 60% is 6 over uh, 10 times 12, so you get 7.2 volts. So again, applying the same formula, you have V is equals to K omega plus IR. And now you're supposed to find the speed. Okay, and the speed is this omega over here. So what we know, the voltage is 7.2 equals to K omega plus IR, which is 4.517. Okay, so from there you can substitute you can find for k omega, and you know what is k, so you can find omega. So omega you'll get as 89.4 radians per second, and then you need to convert it to RPM. Okay, which will be 8/4. So the answer here is C. Okay, so that is your first question here on motors. Okay, so for the second question, a PMDC motor is powered by a 24-volt DC supply. When the motor current is 0.5 ampere, it spins at 3000. When the motor current is 0.8 ampere, it spins at 1002. So what is the torque constant? Okay, so this is very similar to one of the additional practice questions. Okay, so we know that V is IR plus K omega. So the first thing is, when it's at 24 volts, you get 0.4 R plus K omega. So omega here is 2 pi 3000 over 60. Okay, and that will give you equation 1. Okay, and for the next one, it is again 24 volt equals to 0.8 R plus K. So that is when current is 0.8 ampere, the motor spinning at 1200. So 2 pi 1200 over 60, that is your equation 2. All right, and then it's just simultaneous equation, so you can just solve it. Times 2 minus 2, what you will get is 24 equals to K 100 times 2 pi over 60. Okay, and then you can get K to be 47.7. Okay, so in this question, basically you're given two sets of information, and then you form two equations, and then you just do simultaneous equations to solve it. Okay, in this third question, PMDC motor is powered by 24-volt DC supply. Its rotor coil resistance 22.5 ohm. What is the current drawn by the motor when it's providing maximum mechanical power? Okay, so if you were to draw again your supply, this is your 24 volt. Okay, so you have your resistor and your motor here. Okay, and the core resistance is 2.5 ohm. So we know that when current is flowing, there is a voltage drop across the resistor plus there's a back EMF voltage. Okay, now for you to deliver, so if you think about it, all right, if you simplify it to say that it's equivalent to two resistors in parallel, because both of them are just consuming some power. Okay, R1, R2. This is actually very much like how you would do your Thevenin's equivalent circuit. All right, so if you remember your Thevenin's equivalent circuit, you have a voltage source and a resistor, and you have a load attached to it. All right, so if this is 24 and this is R1 and this is R2, all right, so this is considered your Thevenin's equivalent circuit and this is your load R2. And your maximum power transfer theorem says that you will have maximum power when your load resistance is equivalent to your Thevenin's equivalent resistance. Correct? When R1 is equals to R2. Okay, that means effectively the voltage drop across both R1 and R2 must be the same. That is when maximum power transfer is delivered. Correct. So in the concept of resistance, we say they are both the same. So when the resistors are the same, that means the voltage drop across both of them are the same. So if you apply that concept back over here, for maximum power to be delivered to the motor, the voltage drop across both of them must be the same. So I must have 12 volt here and I must have 12 volt here. Okay, so if I'm going to have 12 volts across the resistance, okay, of the across the resistor over here, so the current that is flowing here will be 12 over 2.5, which is 4.8 ampere. So the current that is drawn during maximum power transfer is 4.8 ampere. Okay, so that is how you look at this question. Okay, so next one is quite straightforward. Okay, not much to be concerned about. So you are having two transformers. Primary is 14 ampere, and here is secondary is 2 ampere, and you're given that the primary winding is 120. Okay, so again the formula is as before, NS over NP is equals to UIS. So basically you get NS is equals to 840. Okay, so you just substitute the values in, okay, for the relationship, and then you get the final answer here. Okay, so nothing much to discuss about over here. Question 5 is also very similar, straight off the notes, where is again relating the voltage ripple to the parameters, the load voltage, the frequency, resistance, and capacitance. Okay, so in this case, the voltage ripple is 0.4. You have 8, okay, 260, this is 20, and then you have C. So from there, you can calculate C to be 8.33 millifarad. Okay, which is this. Okay, so let me go on to the next question, question 6. So in this question, the input power at the, so again a transformers question. So okay, so you have input power of 1200 watt at 200 volt RMS, and the secondary current is 1.5 ampere RMS. The number of turns in the primary winding is 50. So we're supposed to calculate the secondary voltage. Okay, so as before we said, primary power and secondary power is the same. So primary power is 1200 watt. Here should be 1200 watt as well. So basically what you have is 1200 divided by 1.5 is 800 volt RMS. Okay, so of course, one of the things you might want to be careful about is one of the things that you can be tricked is if, let's say, one of the voltage is given as peak, the other one is given as RMS. All right, then you must make sure everything is consistent. All right, so if everything is peak, then it's fine. Everything is RMS, is fine. All right, but if one is given as RMS, one is given as peak, then you need to make sure everything is consistent. All right, so either you convert all the RMS to peak or peak to RMS, whichever way, to do the calculation. All right, so you must make sure that you do that correctly. All right, when you are doing these equations. Okay, so for question 7, exactly the same as before. Exactly the same. All right, no difference at all. Okay, only thing you have different frequencies. So again, the same thing. You have a band pass filter where the lower cutoff is 1200 and this is 4500. So this is your cutoff for your high pass filter and this is your cutoff for the low pass filter. Okay, so in terms of formula, FH is 1200, which is equals to 1 over 2 pi R2 and 1 nano. Okay, because this is your high pass filter and this is your low pass filter. Okay, so from this you can calculate your R2 to be 13269, and then for the low pass the cutoff is 4500, which is 1 over 2 pi R1 100 nano. Okay, so your R1 will be equals to 354 ohm. Okay, so R1, R2 over here. So R1 is 354,132. So the answer here is B. Okay, so that is basically again same as your previous paper question. Okay, so question 8, again exactly the same. Right, exactly the same. Only thing numbers are different. Okay, so you have a signal, all right, where the frequency range that you're interested in is 194 to 540, and then you have noise, okay, somewhere here at 8K to 13K. Okay, so you have some noise over here. So what you want is you want the noise to be reduced by at least 15 dB. So the 15 dB, minimum 15 dB must be achieved at 8K. All right, so you're going to design a low pass filter. It's going to come like that. All right, so the only thing is the same as before, so I'll not go through all of it again. The pass band gain you don't need to touch because that is constant. It does not change with frequency. The component that changes with frequency is the second half of the equation, so that is minus log 10 root 1 plus omega RC squared. F equals to 8K must be equals to minus 15 dB. All right, then the rest is the same. Okay, equals to 5.623. The RC is 1.1 times 10 to the power minus 4. So that will give you a combination of this 11K and 0.01 microfarad. Okay, so of course, the alternative, what they might ask you is instead of a low pass, you must use the high pass. If I'm using the high pass, all right, is the equation the same? Yes or no? No, the equation is not the same. All right, let me just bring up. Okay, maybe later I'll bring up. Okay, so I'll continue this first. If you look back at the tutorial questions, there's one question where we came up with the same expression for high pass filter. Okay, so high pass filter, the expression is different. Okay, so if the same question, all right, I flip it around, okay, and then I say that this is what I want. Okay, if I say that this is what I want, and I say that this is noise, all right, that means I must make sure that and I say I want the noise to be reduced by 15 dB, okay, then which frequency must you look at, 195 or 540? Okay, so it's the same thing. Okay, so let's just say I give you the same scenario here. Okay, this is my noise. Okay, so now this is my noise, 194 and 540. All right, and this is what I want, 8K to 13K. And I say I want the noise to be reduced by at least 15 dB. Okay, so this 15 dB, so of course this expression here is different. All right, that one you can look back at the tutorial later to revisit the expression. Now, when I say it must be reduced by at least 15 dB, so which frequency must I look at for 15 dB? Should I look at the 195 or should I look at the 540? Which one should I look at? Okay, I should look at the 540. All right, why? Because the high pass filter is going to look like this. Right, this is the band pass portion of it, and then it will be coming down here. All right. So this point here is where the difference must be at least 15 dB. Okay, so at 540 already, I must be at least 15 dB. Anything before 540 will be lower than 15 dB. All right, so it's the same thing. Only thing is I use a different formula and I must choose the correct frequency. All right, so that is probably one way they can change the question. All right, and sort of you still do the same thing, but it's different formula and a different frequency you need to look at. Okay. Okay, so let's go on to this question. Okay, so in this question, calculate the value of V out. Okay, so what is the value of V out? Okay, so let's look at it step by step. So the op amp here plus is connected to ground, so this is also 0. All right, which means I can calculate the current. So this current here I is equals to 4 minus 0 over 10K. And this same current is a current that is also going to flow through here. Correct. So the voltage, okay, so whatever current flowing through this 10K resistor is the same current going to flow through this second 10K resistor. And the voltage that is going to be here after the second 10K resistor is 0 minus, okay, 4 over 10K multiplied by 10K. So this is basically your IR, okay, the voltage drop across this 10K resistor. All right, and that would give me minus 4 volts. So the voltage over here at this point over here is negative 4 volts. Okay, so now the next thing is what? So if this is negative 4 volts, all right, and we know that no current go into the op amp, so whatever current is flowing here can only flow here. All right, there is no current flowing in the op amp. So you have two resistors here, 10K, 10K. So there is basically a voltage divider. So if it's 10K, 10K here, the voltage at this point is minus 2 volts. Correct? You divide by 2. For the plus of this op amp, you have a 1 volt connected. So the negative for the op amp, you have a minus 2 volt here. Okay. Now, if I look at this op amp, you can see that there is no feedback. Okay, whenever there is no feedback, that means your op amp is connected as a comparator. Okay, that means the V out is not connected back to any of the input terminal. All right, so in that situation, this op amp is actually behaving as a comparator. So as a comparator, basically you can see that V plus is greater than V minus, which means your V out is going to be VCC or VSET. Okay, so of course, since we assume that is ideal op amp, so the output here is VCC, which is plus 5 volts. So your dual supply here is plus minus 5 volts. So this will be plus 5 volts over here. All right, so that is how you analyze this op-amp circuit over here. Let's look at this next one. Calculate the value of I out in figure 3. Okay, so how do we do this? Again, we go step by step, okay, with what we know. So for the positive of the terminal, we can see that there's a 6 volt and there's a voltage divider here. So again, by applying voltage divider, we know that this point here is 4 volts. All right, so if here is 4 volts, then this point here is also 4 volts. All right, so if this point here is 4 volts, all right, what can you say about the current that is going to flow here? Okay, the current that is going to flow here will be I, which is 4 minus 2 over 100k. Okay, which is 2 over 100k. So it's basically your normal Ohm's law. Okay, and since no current flows into the negative, the same current 2 over 100k is the same current that is going to flow in this 200k as well. So the voltage here is basically the voltage at this node here for plus the voltage drop across this resistor. So the voltage drop across the resistor is again IR. I is 2 over 100k multiplied by the resistance, which is 200k. And that will give me 8 volts. Okay, so the voltage at this point here is 8 volts. So the current here is going to be 8 over 600, which is 13.33 milliampere. Okay, so the answer here is D. Okay, so the answer, again, you always have to follow based on the, okay. Okay, so the current that is flowing, okay, you have to remember that current flows out of the op-amp. All right, so out of the op-amp, current will flow. Okay, how much current we do not know, but what we know here is we know the voltage. So current that flows out here is going to go in this part and this part. Okay, and since we know that the voltage here at this point is 8 volts, which is higher than ground, so we know that the current is going to flow in this downwards direction. All right, so since the current is going to flow in the downwards direction and the arrow is also drawn in the same direction, so the value has to be the positive value, okay, which is plus 13.33 milliampere. Okay, so for question 11, again, very similar. All right, you're given a lot of information, but you just focus on what is important. All right, so we have frequency range of 600 to 1000, and you want to enter the Nyquist rate. Okay, so what is the Nyquist rate? Nyquist rate is the sampling rate. Okay, so always remember Nyquist rate is your sampling rate. Okay, which is your Fs, which is your 2 Fmax. So your maximum frequency is 1000 hertz. So you're supposed to sample at 2000 hertz. Okay, so as long as you know the definitions correctly, then there's no issue. Okay, similarly, oh here, this is the Nyquist frequency. So Nyquist frequency is the highest frequency that you want to sample. Okay, so always remember it's the highest frequency you want to sample, because in the question you can have a lot of different frequencies, that is fine. But what is the frequency you want to sample, the highest frequency you want to sample? Okay, so let's look at the question. A deep C frequency microphone has a maximum sampling frequency of 150. All right, the optimal frequency is again 3 to 40. So what is the sample by AI system to isolate the optimal signals and further study? So what is the Nyquist frequency of the deep C microphone recorder? So if I'm sampling at 150 kilohertz, so okay, so if my Fs is 150 kilohertz, that means my Fmax kilohertz. Okay, so that means the Nyquist frequency is the highest frequency that the system can sample. All right. So in this case, it is half the sampling rate. Okay. So again, what is the Nyquist frequency of the deep sea microphone recorder? All right. That means for the microphone recorder itself, the sampling frequency is 150 kilohertz. That means that is your FS. That means the Nyquist frequency of that particular recorder is 75 kilohertz. That means as long as your input signal has a F of 75 kilohertz at the maximum value, you can still use this particular microphone. Okay, so that is the thing you must understand. Okay, so again, the 3 hertz to 40 kilohertz is there to divert your attention. Right, what is important is your microphone here is sampling as a maximum sampling frequency of 150 kilohertz. So the Nyquist frequency of the microphone recorder is 75 kilohertz. Okay, 75 kilohertz. Okay, so let's look at this question here. So here we are given a op-amp. So calculate the value of V out. All right, so let's look at it. So if again this is a closed loop op-amp, so if V plus is ground, then this is also ground. Okay, so with that you can calculate the current. So this current here would be 3.2 over 500, which will be 6.4 milliampere. All right, so since no current flows in, the same 6.4 milliampere is also going to come here. Okay, so the voltage at V1. Okay, so what is the voltage at V1? So here is 0 volt. All right, so V1 will be equals to 0 minus the voltage drop across the resistor, which is 6.4 milli multiplied by 1000, which will be equals to minus 6.4 volts. Okay, so V1 is minus 6.4 volts. All right, so if V1 is minus 6.4 volt, then I know that the resistor connected to ground, so the current is going to flow in this direction here. Correct, because ground is higher than negative 6.4, so the current is going to go in this direction. So this current over here is 0 minus 6.4 divided by 800, which will be 8 milliampere. Okay, so 6.4 milliampere is coming in through this branch. Okay, another 8 milliampere is coming in through this branch. So the combined current that will go out here will be 6.4 plus 8 should be 14.4 milliampere. Okay, so if 14.4 milliampere go out here, so what is V out? Okay, so V out is whatever is at V1, okay, subtract the voltage drop across the 400 ohm resistor, correct? So what is V1? V1 is minus 6.4 volt, subtract the voltage drop across this resistor, which is IR. So I is 14.4 milliampere multiplied by 400 ohm. Okay, so that will give me minus 12.16 volt. Okay, so the answer here would be B. Okay, so question 14. Okay, so here we are given that we are using a temperature sensor. Okay, and we want to cut off the supply when the water boils. Okay, so the output of the LM35 increases by 10 millivolt per degree centigrade. So she needs to cut off the signal voltage to be around 3.3. All right, so let's look at it. So we know that at 0 degrees Celsius is 0 volt. Okay, so every 1 degree Celsius it increases by 10 millivolt. Okay, which means that if I go up to the boiling point, 100 degrees Celsius, it will be 1 volt. Okay, so that is for the sensor. Correct, that's for the sensor. So it starts off at 0 volt at 0 degrees. It increases by 10 millivolt for every 1 degree Celsius. So at 100 degrees Celsius, it becomes 1 volt. Okay. Now, what we want is we want to cut off the signal, all right, when it reaches 3.3 volt. All right, and the 3.3 volt must match the point when the water boils, which is this. Okay, that means as far as we are, what she wants to do is the sensor is giving her a reading of 1 volt when the water boils. But we want to design the circuit such that when the water boils, I get a reading of 3.3 volts. Okay, so the gain that I need here, the gain here must be equals to 3.3 over 1, which is 3.3. Okay, and she's designing a non-inverting amplifier. So 1 plus RF over RI must be equals to 3.3. Okay, so RF over RI must be equals to 2.3. And the combination that gives you that is this RF3K and RI 1.3K. Okay, so that is for question 14. Oh, okay, so for question 15 over here, basically very similar. Okay, but what we have now is we are given, all right, that we want LED to light up. Okay, so the important thing is the distance. So the distance is 5 cm. Okay, so for 5 cm, if I were to draw the line here, it goes up to okay, so it's around here, so it's around 3 point it's somewhere between there, so it's around 3.83 3.84 around there. 5 cm is around 3.83 3.84 volts, okay, around there. So what we are given here is we found 3 potential circuit, okay, and which one will you use? So the idea is he needs LED 2 to be lit when an opaque object is more than 5 cm. Okay, so it's more than 5 cm. All right. So the resistors are already given to us. Okay, 100 and 330 is already given. So we know that that gives us a value of 3.83 something. Okay, so the voltage here is around 3.83 volt. Now what we want is when it's bigger. Okay, so if my voltage is bigger than 3.83 volt, okay, which means my distance is greater than 5 cm. Correct? All right, so that is the first thing you must know. Okay, voltage bigger than 3.83 volt means distance greater than 5 cm. Now, if this condition is satisfied, you want, if this condition is satisfied, you want LED 2 to light up. Okay, if not, LED 1. Correct? So that is the two conditions you must understand. Distance greater than 5 cm is LED 2, and distance lesser than 5 cm is LED 1. Okay, so now let's look at the first circuit, circuit A. Okay, so we know that the voltage at both these 2 points is 3.83 volts, okay, which corresponds to the 5 cm mark. So when my voltage here, okay, so this 2 op amp, for the second op amp here, the signal from the IR sensor is connected to the plus. So when V plus is bigger than V minus, all right, then LED 2 lights up, which satisfies this condition here. Okay, and if it is lesser than, okay, so when my signal distance is lesser than 5 cm, LED 1 will light up. So this condition is satisfied. So circuit A can. Okay, circuit A is a valid circuit. It works. All right, now let's look at circuit B. When I look at circuit B, what do you see? You see I'm using now a single op amp, and the reference point here, which is connected to the negative terminal, is 3.83 volt. Okay, so when my Sorry. This is not 3.83 volts. This is the signal from the sensor. The reference here is this V plus. So the V plus is connected to 3.83 volts. All right. So when my 3.83 volts, okay, when my signal from the sensor is bigger than 3.83 volts, okay, when my signal from the sensor is bigger than 3.83 volts, which means your V minus is going to be greater than V plus. So when V minus is greater than V plus, what happens? You will go into negative V set, correct? Because it's a comparator configuration. So I'll go to negative V set. So if I have a negative V set here, all right, what will happen? Since my anode is connected to the ground, my current will flow through LED2, LED2 will light up, correct? LED1 cannot light up, all right, because it is uh, yeah. So LED2 will light up, all right, because it is going in this forward direction. LED1 will be considered as reverse bias, so it will not light up. Okay, so only LED2 will be lighted up. So that satisfies this condition over here. Now, the second condition, when your V minus is lesser than your V plus, if V minus than V plus, then I'll go to positive V set. Okay, which means it is the second condition, distance is lesser than 5 cm, then my LED1 will light up. Okay, because current will flow in this direction. Okay, current flow in this direction, LED1 will light up. So the second condition here is also satisfied. Okay, that means circuit A also can work, circuit B also can work. Now, for the third circuit over here, again, you can see that the positive is connected to the 3.83 volt reference. So when my signal here, V plus is bigger than V minus, what will happen? I will go into, when V plus, okay, so in the condition where my signal, okay, is bigger than 5 cm, that means bigger than 3.83 volts, this will go to a negative V set. So when this goes to a negative V set, what will happen? Okay, current will flow through this branch over here and light up LED1. Okay, which is not what I want, because when it's bigger than 3.83 or bigger than 5 cm, I want only LED2 to light up. All right, but now I'll cause current to flow through here, LED1, and also to LED2. So both the LED1 and LED2 will light up. Okay, so the circuit is not going to behave based on the condition that we have. Okay, so the only two circuit that actually fulfills the requirement is circuit A and circuit B. So only B here is the answer. Okay, understand what is connected to the positive. All right, so that discussion here. Okay, so any questions you all have for the discussion so far? Okay, so I think okay, for if you haven't done your revision yet, okay, when I upload the video, you can refer back to this, all right, to recap and see whether anything is missing. All right, for tomorrow, all right, but I will still come in. Okay, if you have questions, you can ask me for any clarification. Okay, if there's nothing to ask, that I will be going through. Okay, we already gone through all the practice questions are already out there. Okay, you can try them, and then the quiz answers and quiz discussion we had it today. All right, so there's nothing new to go through tomorrow. Only if you have any doubts that you want to clear or anything you want to ask, you can ask me. All right.
Oh, Prof. Yeah, for the formula for power gain, you use this formula 10 log 10 PR over P. Is it like true for, like, is this a general formula that you can use for all instances? like P out over
Yes.
P in equals 10 log 10.
Yeah, 10 log P out over P in is the power gain.
Also, we can either use this or we can use the voltage, the V out over V in of 20
Yeah,
log frequency.
yeah, that is 20 log. Yeah.
Oh, uh, for Prof, I don't get it, right? Because when we're finding the gain, why do we need to convert the rectangular form to like the polar form, like the magnitude? Like, why do we take the magnitude for?
Because the magnitude is the component that gives us the actual gain, correct? There's the magnitude and phase. The phase does not, we don't factor in the phase when we're calculating the gain. The gain, we use only the magnitude part of it.
Oh, okay, so get it. But then another thing, one last question is Prof, for the loading effect, I don't get like how does first for the loading effect, let's say there's a high high pass filter in front and a low pass filter behind. Then I don't get like why do we have to like take how does the loading effect like affect the voltage at this point? Because won't the voltage itself get affected by the RH area? Like since the voltage will get attenuated, will get reduced based on the frequency. Then what difference does it make if
Yeah,
there's a
correct.
loading
So
effect?
the filter reduces the gain based on the frequency, but because of the fact that there is another resistance, another impedance path parallel to the current path, it does have, so that's why it's called a loading effect. That means it is a side effect of your circuit. It is not the intention. All right. So because you have two parallel paths of impedance, all right, the current always takes the path of, so when you have two parallel paths of impedance, then the combined impedance will be that towards the lower impedance. All right.
Oh, so if there's a loading effect, it will cause the cutoff frequency. It will cause it to cut off wrongly since the entire the resistance in the high pass frequency will get affected by the low pass frequency. So the whole equation sort of changes. Is that what the effect is in that sense?
Yeah. Yeah. Correct. Yeah. So I mean, we're not going to the details, but basically because of loading effect, the impedance on the circuit will not be what we perceive it to be. So that's why we need to sort of clearly separate out the high pass and low pass filters.
Because otherwise the high pass filter will cut off wrongly in that sense.
Yeah. Yeah.
All right, understand. Thank you very much.
Okay. So there are no other questions. We can end here. Have questions, you can ask me. All right. If not, then I'll see you all on Monday for the assessment.